This video has been supported by PCBWay. Hey guys, NNN is only just starting, but I'm afraid we're all failing today. Time for some volt nutting. We are getting pretty close to having touched all 8.5-digit multimeters. And if this is what I think it is, we are getting one step closer still. A little warning up front though, this will probably not be the thorough in-depth documentary that this legendary specimen deserves. It's only passing through geographically on its way from one friend to another for a quick test and calibration. So I don't want to delay it any more than necessary. And anyway, we've seen the successor, Fluke 8508A, and the autistic savant sibling, Wavetek 4950, both having large technological cross-sections with the one and only Model 1281 self-cal digital multimeter. So let's get started right away. I'll see you at the ppm tower. This is the last time I'm milking this joke, promise. The lower multimeters are at their load-bearing capacity, I'm sure. And this is a more convenient location for testing anyway. 1281's user interface is mostly familiar, of course. In these meters, AC voltage, resistance, and current are optional options. The lucky unit in front of us is equipped with all three. So there is a lot of testing and, depending on the results, a lot of calibrating ahead of lucky us. The 10-volt DC range is only 5.7 ppm out, so that's promising. A fast self-test reveals a reference error 2132, which the publicly available documentation translates to an internal reference 2 being outside of an allowed voltage range. So there are two LTZ1000 modules in here, and number 2 seems to have a wrong voltage. How unusual. A full self-test is cheekily refused to us with similar reasoning. It wants to calibrate its internal sources first. That's routinely done only after performing external adjustments. Here's why. Let's say we send this to a cal lab. First of all, they are relieved that the customer didn't forget to include the key for what is usually the calibration enable key switch. They show our meter what a real 10-volt source is, and it adjusts its own gain and offset parameters. After that, the meter offers to use its newly adjusted faculties at their highest accuracy, to check on some built-in high stability standards and to memorize their values. In the future, it can use those again to realign its less stable parts and ultimately earn that self-cal title. Alas, once again we are seeing a question mark, prophesizing an unsuccessful internal source cal. 2132 again, incorrect magnitude of that second voltage reference. So that puts us in a bit of a pickle. That error will hinder a lot of the functions that make this meter special. And it looks like additionally higher frequency ACV readings are 6% out. Any attempts to adjust away such a large deviation are met with a 2001 error, probably out of adjustment range. That is with all participants having been warmed up for hours, with a purpose-built, short, low capacitance test lead set, and double-checked with other meters. That requires a look at the hardware to fix, unfortunately. I would be overly enthusiastic about this normally, but the meter's new owner is an enthusiast too, whom I wouldn't want to rob of all the enjoyable troubleshooting. Then again, calibrating only half the meter, and not even the internal references, would be a bit of a waste now that it's here already. How about this? I try to fix what I have to, calibrate, and then I get creative and hide a real mean, intermittent, unexpected fault somewhere else. No? Let's look at the 2132 error first. This test expects between 0.7 and 0.74 of a full-scale reading. After connecting a reference to the ADC with multiplexer M401, that is a DG508, so we are interested in its output, which is pin 8. It seems to reside right next to the flying spaghetti monster over here. As always, we can enter the self-test configurations manually and probe the circuitry while observing what the ADC is putting out on the meter's own display. A full-scale reading is 1.999999, or let's say 2, so that I don't have to speak so much German, whenever it sees a 10-volt input. So when seeing the healthy, normal -7.14 output from voltage reference module 2, the ADC reading seems reasonable to me. Now the other Vref module seems to be putting out 7.3 almost. That is also within the allowed range of LTZ 1000s, but there is a pretty large discrepancy between the two. I believe we could put some distance between us and the self-test failure limit by bringing the voltage references closer together. I'll have you know, I always keep some emergency LTZs within arm's reach, and I wouldn't be afraid to try one here. But these old Datron modules are probably handcrafted and fine-tuned and consecrated by nude Englishmen. So I'll have to ask the owner before touching those. We do seem to have a pretty large datecode discrepancy on the LTZ parts themselves already, with most of the remaining meters datecodes being late 90s, and no colored dots on the metal cans. For reference, the corresponding module in my 4950 seems to be putting out closer to 7.3 volt too. You know what? Soldering on the outskirts of these modules will not disturb the LTZs significantly. So let's perform a quick risk-free transplant to see if I have identified the root cause of the problem here, or if I'm wasting time contemplating LTZ swaps while it's actually something else entirely. And there we have it, the famous module of no tolerance. This is my first time having one in hand. I'm surprised to see a bodge on this widely reused 80s design, in a seemingly late 90s meter. The same thing and another patch in the swap candidate from Wavetek 4950. They must have been super reluctant to change this layout. Understandable, its great performance is the foundation of some of Datron's best products, and they did design a significantly better LTZ 1000 implementation than the datasheet default that Hewlett-Packard used. The central Vishay-branded T05 part is actually home to 5 bulk metal foil precision resistor chips. And this module can become a negative 7 volt reference simply by moving 3 jumpers. From this perspective, they all need to be in the up position for use in 1281 multimeters. Wavetek 4950 expects a positive 7 volt reference, so they were all in the down position. I suspect that not many are going to fondle these modules voluntarily, so while I was in the neighborhood I took it upon myself to measure some temperature coefficients and low-frequency noises. It's not much, but I'll push the results on GitHub, link below. LF noise seems to be degraded slightly when tested in circuit, so these two seem a bit high, but the one I tested standalone seems normal for an LTZ 1000. With the right module swapped, we now have excellent agreement in here. And if my theory is correct, that should eliminate the 2132 error. A fine-tuned, tastefully aged Datron voltage reference module is great, of course, but with a little help from my sponsor PCBWay, I'm trying something new. This innocently looking SMT part contains one of those boards, plus output scaling and overall temperature control. It could be great, but the SMT mounting style has some thermal and mechanical disadvantages over traditional leaded packages. It deserves to be investigated if those matter at all, but in this case I've asked PCBWay to create some flat, flexible leads for me. With the growing popularity of flat flex circuit boards, PCBWay's prices and processing times are falling, while their quality is better than ever before. Get an instant quote for your PCB, FPC, assembly or other rapid prototyping services at the link below. And perhaps also take a look at PCBWay's 7th project design contest, where you can win cash and hardware prizes to boost your open source project to the next level. It's happening right now. More details about ADR 1001 soon, TM. Let's have a look at the ACV issue next. I'm using an arbitrary waveform generator to put out 1 volt RMS, and I'm only changing the frequency between 1 and 100 kHz. I'm sending that to the surgery area through this long-ass BNC cable. Even at this length, I don't think any coaxial cable would attenuate a 100 kHz signal by 6%. So this is the problem we are having. I also checked that all ACV ranges are similarly affected. So while there are dedicated per range high-frequency trim potentiometers, I find it unlikely that somebody would take the time to mess them all up equally. Never mind, found something a little bit closer than the long-ass BNC cable. I'm now using the scope's built-in waveform generator, and I've connected it to the meter's front input. With ACV selected, that gets routed to this connector on the AC board. All ranges from 100 mV to a kilovolt have to go through the attenuator, which is basically resistive for DC and low frequencies, and parallel capacitors take over at higher frequencies. Nothing should be broken there, unless there's been a huge catastrophic overload. But after that comes a pretty complicated preamp, the schematic of which takes up an entire page. This guy would be in a position to influence all ranges equally, so I'm going to scope probe its output and perform the same 1 to 100 kHz frequency sweep, while recording the RMS value of the output. That could be done with most remotely programmable oscilloscopes nowadays, but Keysight's HD3 series has a frequency response analysis tool for that. That makes it a bit easier by auto-scaling X and Y and by plotting the results in decibels. And yeah, this preamp certainly is very frequency dependent. I think there are other correction mechanisms outside of it, but again, just seeing how complicated this sub-circuit is, I can't believe that this is its normal healthy performance. This must be our culprit. Here it is. It sure looks uninviting, doesn't it? Fundamentally, it's just an inverting amplifier where lower feedback resistors are switched in for higher voltage ranges. That and a million little tweaks and optimizations for flattest frequency response. Down here we've got the equivalent of HP 3458A's flatness DAC. Remember? We had business with that one once upon a time. This whole segment is basically just using a JFET as a variable resistor that allows the control logic during calibration to ever so slightly tweak the preamp gain by sneaking a small part of the output past the normal fixed feedback elements if needed. And then actually through this 560 femtofarad capacitor into the summing node. That means that this mechanism can only act on high frequencies, and that is what piqued my interest in it. That just matches our odd frequency response behavior too suspiciously nicely. Sure enough, there is something wrong here. The digital to analog converter can only put out positive voltages, so there is no healthy way for the op-amp output to be railed positive. To save some time, we can skip all the head-scratching and fact-checking of the published drawings, and the part where I tried a new op-amp and a new JFET pair, before finally discovering this broken PNP transistor that was maliciously leaking something negative out of its base, effectively disabling this whole part of the circuit. With that part replaced, we should be back in business, but there is one more thing. The ACV preamp frequency response is now flatter, but all flattery aside, the gain far below 1 still has to be wrong. And there seems to be a fair bit of superimposed noise exactly until I connect the oscilloscope's ground clip somewhere. I have no idea how this hasn't caused much more severe problems earlier. But further investigation revealed that the front low input is not actually being connected to Mecca, the central 0-volt star ground point, as it should in voltage modes, not so much in ohms and current modes. So without the ground clip we were just relying on leakage or capacitive coupling over protective earth or something. The only things between front low and Mecca are a jumper link which doesn't wear out under normal circumstances, and relay 108. I'm going to go with relay here, or relay control circuit more specifically, because choosing the rear inputs, for example, should flip some other relays, but there is absolutely nothing happening. The single coil latching relays that I used in here are held at about 7 volt on one side all the time. On their other sides wait these HEF40 244s, which are tri-state output 15 volt capable push-pull drivers. So their output pins can either be high impedance to do nothing, push 15 volts in to flip, or pull to ground to deflip, or the other way around. Various 74 series flavors of this chip still exist, but this high voltage capable variant seems to be mostly obsolete. That must be part of the reason why Fluke used operational amplifiers for the successor of this circuit. Sadly, I have none of these in stock, and there's a stupid holiday where I live, and then a weekend after that. I couldn't possibly wait that long. So today it is my great pleasure to announce the first product from Rep's semiconductor division. A highly reliable, non-obsolete drop-in replacement for HEF40 244s. Fluke, give me a call if you need some. With that installed and the voltage references equalized, I'm reasonably confident that our initial problems are solved. So I'll quickly let the calibrator adjust itself to my latest and most trustworthy standards, and then the multimeter gets to adjust itself to that. I wrote a Python script that goes through all the functions and ranges and adjusts them to the calibrator. It's checking for failures between each step, but it looks like this time we are getting through all the way. This is a long process, but I don't think I'm going to let it run overnight or while away. There are kilovolt ranges involved, and I'd like to be able to intervene when something starts to fizzle. Nothing did. This looks like a mission accomplished. Another happy customer, or, well, we'll see about that, when he sees that I solved the tastiest problems. The meter is also passing its internal source cal program without complaints. And after that the full self-test as well, which it refused to even attempt before. I'll consider this job done, but we still have a couple of minutes before this high-profile patient needs to continue on its journey. So I set up a couple of DC voltage sweeps to be observed by 3458As and Datron 1281. The raw results are linked below, but my TLDR so far would be that Datron's integral linearity is within 0.2 ppm of the best linearity that my lab has to offer. With the ADC consisting of discrete components and the schematics being out there, this can and will be fine-tuned to perfection by the new owner, I'm sure. I also ran a slightly modified script from the XDev's archives. This was originally meant as an all-round comparison for Model 4950, so the pass-fail limits are not suitable for our DUT today. It's actually a lot looser around the ACV and ACI ranges. So the small red numbers are okay, and what few excessively large red numbers we see can be explained by a settings mismatch, such as a default 100 Hz high-pass filter. What I'm saying is I don't think there are any more hardware defects. This is all good. The aforementioned flying spaghetti monster, this multi-tap epoxy-infused toroidal transformer, is a fascinating feature in 1271 and 1281 multimeters, and yet the official documentation tells us virtually nothing about it. It is the linchpin of its self-cal capabilities, while 3458A simply relies on its linearity to self-cal its 10-volt range based on its 7-volt reference. This guy relies on the ratio of the transformer windings to derive various voltage levels from its references. I think it's only used to generate ±10 volt and ±1 volt in this series of meters, but the concept is solid and could be applied universally. They are chopping up the reference voltage into a square wave, which then excites the transformer. Then they can choose which secondary winding to tap into and which half waves to rectify. Only the positive? Only the negative? Mix and match to generate intermediate voltages? Either way, number of windings don't have temperature coefficients or long-term drift, so this will forever be as stable as the LTZ-1000s. Closing remarks. I might be easily impressed with high-resolution multimeters. I love them all. I love this one especially because of its silent, cool operation. Even though it isn't rocking a cooling fan, the outside of its enclosure doesn't get much warmer than 33 Celsius or so. Fluke 8508A on the other hand, I've seen it over 40 in a 23 degrees Celsius environment. In that case, one really has to be careful with workbench layout and packing density, so that temperature-sensitive devices don't influence each other. I love the dual display user interface, much more usable to the uninitiated than 3458A's solution. I love the software selectable rear inputs if they work. It's a miniature built-in scanner card. And while there are special, nearly irreplaceable ICs fitted, I love that there is no notoriously drifty steering hybrid that you have to worry about 24/7. This one is repairable in most cases. I'd like to adopt one of these myself one day. Currently on European eBays there are two 1281s for sale, for around 3,000 gold. Yeah, no, I don't love it enough to consider that kind of investment. For that it would have to have much better AC performance and 3458A-ish DC linearity. But yeah, iconic overall. Glad to have some hands-on experience.